So welcome to 2015 question C1. The accompanying map located on the back of section A. So this is our map here, it's on the back of your short questions. Shows ground contours at 5 meter vertical intervals. So how you approach these questions? Straight away, check the vertical intervals. Then you go down and you check the scale. Scale is 1 is to 1,000. So 5 meters equals 5,000 millimeters divided by 1 is to 1,000. So divide by 1 here, and then this one divided by 1,000. So 5 meters equals 5 millimeters on our sheet. Okay, so that's the first approach to these questions. 5 meters equals 5,000 millimeters in real life. Divide by scale. 1 is to 1,000. 5 meters equals 5 millimeters. So ABC is the centre line of the proposed roadway. DEFG is a car park. The roadway has the following specifications. ABC roadway. A to B is level at an altitude of 65 meters. B2C is rising uniformly to a level at 70 meters at C, and DE and GF of the car park are level. Using side slopes 1 in 1 for the cuttings and 1 in 5 for the embankments, complete the earthworks necessary to accommodate both the roadway between A and B in the car park on the northern and eastern side. So the earthworks on our southern side have already been done. Right, so we'll look at our map. So A to B is at 65 meters. Now, look. So this is where the 65 contour hits the road, and that's where it's going to change from cuts or embankments, right? Where the numbers are lower than the level of the road, we have an embankment. Where the numbers are higher than the level of the road, we have a cut. So there's a cut there on the southern side, there's an embankment on the southern side. So there's going to be an embankment here and a cut there. Now I'll start by dealing with the embankment. So the side slopes are 1 in 1.5. Now this is a good approach too. So I'm going to sketch out basically an end elevation of the road, 65 meters here. Here's some of the ground, so 60, 55, 50. And for every 5 meters I go down vertically, I go out 7.5 meters. Out 7.5 meters. And that point there is a point view of a line, and the line pierces the 60 contour. Then when I go down to 55, I've gone down 10 meters. So I'm going out then 15 meters. 15 meters there, because 10 by 1.5 is 15, and that's the point view of a line that pierces the 55 contour. Okay, so we'll start doing it now. So the embankment. So I'm going to mark every 7.5. That'll be plenty. Sorry there. So for an embankment, ground contours get lower in numerical value the further out from the road. So 60, 55, 50. Okay, so there's 65. Here's 60, 55, 50, 50. So we can freehand sketch them in. So a little slight rise in the curve there. It's going to go off to the direction of 55. And there's our embankment done there. Then for a cut, okay, we'll sketch an end view of the road. So here's the ground rising there, 70 rather, 75, okay, 80 or whatever. And then the side slope is 1 is to 1 for the cuttings, 1 in 1 for the cuttings. So when I go out, what you call it, 5 meters in real life, or technically go up 5 meters first. Okay, I've gone out 5 meters from the edge of the road. So each of the lines are the lines here that appear as point views. Okay, they're 5 meters apart. So we'll start a cut. Oh, there's the 65 contour right there, so it's going to start right at B. So for cuts, the numbers get higher in numerical value the further out from the edge of the road they go. So 70, 75, 80, 85. There's no need to do all of them. Okay, so here's the 70 contour. Cut twice, and the 75 contour cut twice. I can freehand sketch them in. fix that a little bit. And the tadpole swims away from the road. Right, so then we'll do F to G. F to G is level, all right, and then we have contours, right? It's level at an altitude of 65 because B is at 65, and line B to G, okay, if it was drawn in, would appear as a point. So G to F is at 65. So we have 65, 60, 55, 50, and 50. So this is going to be an embankment. So we're going to mark a line 7.5 apart. And that's plenty there. So these numbers will get lower in numerical value. So 60, 55, 50. Right, so our first contour at 60, okay, so 60, we'll follow along, is here. Our second contour at 55 is here. 50 is here, then there's another 50 here, and then we're marking 55 and 60 because it's going to have to intersect with the cut for E to F, which we don't know yet. Right, so we don't know that one yet. Then we can lightly freehand sketch these in. Slight rise there. Okay, and then we'll have it in. We'll find the intersection there shortly. So B to C of the car park. All right. So B to C on the map is rising at an altitude of 65 to 70 at C, and the edge of the car park F to E is parallel to that. Now, so we're going to need a cone for doing rising or falling surfaces. But the question is it a cut or an embankment? And this is what I find my students find the most difficulty with, right? They're not sure whether the road is going to need a cut or an embankment, because to see this is 65 and then to see a 70 contour, or they see other questions where the road is maybe a 70 contour was here, and they're just not sure whether it's a cut or an embankment, whether the surface is above or below the ground. So what I like to show students is you don't have to do this, all right, but if you take a vertical profile or a sectional elevation through EF, so you project the endpoints up and you mark where the contours hit the edge of the road, you bring them up and you label the heights here. I start at 50 because that's at 50, 55, 50, 55, 60, 65, 70, and then 75 if needed. Right, now the road goes from 65 to 70, and then look, this is a point on the Earth's surface at contour 50, so I bring that up to 50, that up to 65, or that's at 50, 55, that one, so I bring that up to 55, then I bring this one up to 60, 65, and 70, so on, you sketch them in. So that's the Earth's surface there, and that's the sloping surface of the car park. The Earth's surface is below the car park, so the answer is you need an embankment. Now, the question students have next is the cone. They don't get what is the radius of the cone. Right, how you do this? You find the vertical distance between the 2 points, so 70 minus 65 is 5. Alright, then you sub the vertical height of the cone, 5 meters, into the ratio of embankments. So it's 1 is to 1.5. So then the radius of the cone is going to be 7.5. Sorry, that was a terrible sketch there. Okay, radius of the cone is going to be 7.5. And then the lines afterwards, because they're going in 5 meter vertical intervals, they're going to be 7.5 apart as well. But the distance between these lines, okay, is not necessarily the same as what you call it the radius of the cone. Not necessarily. Now, so we're going to take our cone, and for an embankment the cone always goes at the higher end. So we're going to put it at E, and we're going to set it at 7.5. Now, we're going to draw in our cone now, or our first line, a tangent to the cone. Okay, and then we're going to mark them every 7.5, the lines every 7.5 apart. And the base of the cone, this curve, is at an altitude of 65. So the base of the cone is at an altitude of 65. sorry, so 65, the numbers get lower in numerical value the further they go out from the road, so 65, 60, 55, 50, so 65 is here, 60 is there, then this is 55, this is 50 here, so we can freehand sketch them in. Sorry. And then where they intersect, you join to there, and that's actually a trace, that line. It's a trace between two planes. So that's part A done. So part B, on the map, vertical boreholes, right, that's a very important word, vertical. Okay, P, Q and R reveal the top surface of a stratum of ore at altitudes 35, 35 and 45 millimeters meters respectively. In the space provided at the top of the map, draw the elevation of this triangular portion of the top surface, so technically it's a lamina, and then of the stratum, and determine its strike and dip. So the strike is a level line, okay, on the lamina or on the surface, so it's a horizontal line in elevation and it's a true length plan. And the dip is the angle the surface moves to the horizontal plane, so it's essentially the true inclination of the surface to the horizontal plane. So we can find the triangular portion as a edge, and the horizontal plane will be the x1, y1 line. So our contour here starts at 20, and it went, okay, point O is at a height of 45, so we go as far as 45. So I'm going to mark every 5. Now, 25, 30, 35, 40, 45, and then 50. So it says 30, 35, and 45 meters respectively. So that means P is at 30. So P is at 30. Q is at 35. And R is at 45. So what was it again? 30 for P, 35 for Q. So I'm going to join these together. Now, the strike is a level line across the surface. So look, that's the strike there, just one horizontal line. This could be a strike as well. This could be a strike as long as it's horizontal in elevation. Right, to find that in plan, we're going to just drop the points down in plan. And then we're going to look along the line, okay, Q1 in plan, because it's a true length. So that's the strike in plan, Q1. So there's the strike. Now we're going to take an auxiliary elevation from our triangular portion, so we're going to project parallel to the strike line. And our x1 y1 line is perpendicular to that. And then our heights are marked up every 5. Okay. So I can start this, I will say 20. You can ignore, you're basically skipping all the distance between them. 25, 30, 35, 40, 45. So we don't need to do more than that. Now, P was at 30, okay, Q was at 35, and R was at 45. So we're going to mark them together, we're going to join them together. Now, they need to form one straight line. Now, there we go, might be a tiny bit off, just make do with it. Just look, long story short is you need to have the surface as a straight line. Now, find my protractor. The dip. The dip then is an angle at 20 degrees. should always write it in or risk losing marks. So part C, a lake is located in the area marked L in the southeast corner of the map. So L. The surface of the lake is at an altitude of 50 meters. The line ST represents the center line of an overflow pipe. So the pipe is going to appear as a line from the lake. The pipe travels from point S at an altitude of 50 to a manhole located at T. So that's at 50. Even though it doesn't have a contour line saying it's at 50, and T is at a point there. T is at that point there. The pipe falls uniformly at an angle of 10 degrees. Determine and indicate in meters. So those keywords: determine, indicate in meters. Okay, the depth of the pipe vertically below the ground at point T. So the depth of the pipe vertically below the ground at point T. So T is at the ground height of 40. Now, it says it makes an angle of 10 degrees. The true angle between a line and a plane is seen in the view, showing the line as a true length and the plane as an edge. And if you want to see a line as a true length, well, then you need to look perpendicular to that line. So we're going to essentially project an auxiliary, alright, an auxiliary view of the line ST. It's an auxiliary elevation because it's projected from plan. So I'm going to project up S here, and then I'm going to project up T as well. Okay, my visualizer is on the way. So we can mark up 50 here. Okay, if you want, you don't necessarily have to go down to or through the contour or the earthworks, and then we can mark up 40 from the X1 Y1 line here. Now this is point T. Okay, and then we can what do we have to do then? We have the angle of 10 degrees, so we're going to apply a 10-degree angle from S to the X1 Y1 line. That's critical. It has to be to the X1 Y1 line. So 10-degree angle. Okay, now careful you don't do it going 10 degrees upwards. It has to be 10 degrees sloping down. Now this is the angle of the pipe, the overflow pipe in which it slopes downwards. So that's the angle there. Okay, now it's not the actual overflow pipe. So the actual overflow pipe is well up here now on coming from the 50 meter mark. So it's coming from here. So this is the overflow pipe, and we're asked to mark this depth here. So it's just below 8 meters. Now, the actual answer in that particular year was 8.2 meters. Now, I really think they just use that as a mechanism to dock marks. I don't know, I don't work for the state exam, so I could be wrong. But, you know, if you just mark 8, you'd probably be alright. But that's the depth there. Okay, and that's the question done.